It's a great pleasure to introduce Sheldon Newhouse from the Michigan State University. He's going to talk about the differentiable linearization theorem of Philip Hartman.
Thank you, Jose. So it's a great pleasure to be here at this time in honor of Welington, but also to visit and see some of old friends. You know, Misha Yampolsky said that there was some randomness in it, but he said that he knew Welington. It's a question of how long you know Welington, and it was from the time he was a graduate student, and I knew Welington from the time he was a graduate student, and I wasn't much more advanced at the time at the old building downtown near Praça Tiradentes. What was the name of the street? IMPA. Luis de Camões, right, okay. And we had many wonderful times. One of the things that doesn't usually happen with many mathematicians that he helped me with didn't really have much to do with mathematics, because in my arrival there, of course, what did I know about the Portuguese language? Onde é o toilette? Okay, that's about all I knew. Because that, you can't survive without that anywhere, right? And then they would usually answer and I wouldn't understand, so then they would point and then I would find it. But one of the few people at IMPA who spoke to me in Portuguese at the time, if you call what I said Portuguese as I was learning, was Welington. And so at the T's and other things like that, so he helped me enormously that way. And of course, as time went on, the mathematics became much more important than the language. But the atmosphere there was wonderful, but if I talk about all those old stories, I don't get to tell you the new stories. So I think I'll move on to the new story. So you all know, and I'll remind you here, Hartman's theorem, the famous one, of course, is C0 linearization at a hyperbolic fixed point or a hyperbolic critical point. And that's a very important theorem, of course, and it's quite general, any hyperbolic critical point or periodic point, but fixed point, and then you take the power. But, so it gives you topological information in a neighborhood of the orbit. But it doesn't give you much help when you need differentiable information. And so where this started for me was, first of all, I have an outline, but you'll see the outline. First, I want to say happy birthday, Welington, before I forget. Okay, like that. And today is your actual birthday. So I think we should, right. So, we have to give you champagne and caipirinhas and everything tonight, because as far as the big dinner, don't mix them together. Okay, so where this story started for me was, and this is the simpler version, but was to study bifurcations of homoclinic curves for vector fields, which is a classical subject. You have a one-parameter family of differential equations. Let's start in the plane, and hyperbolic saddle point here, eigenvalues A and B, A negative, B positive, like that. You have the homoclinic orbit, and you have this in a one-parameter family, and you want to understand what the dynamics is as you go through the homoclinic orbit. So you start from this picture where you don't have a saddle connection or separatrix, right? Here I'm assuming now I have a source. So I spiral out. The stable manifold here comes from the source. Unstable of the saddle goes around and misses it. But then you pick it up until it hits, and then you go through like that. This is a classical problem studied in the 30s, around the same time as structural stability, Andronov, Pontryagin. This was Andronov and Leontovich who studied this. And the first time I actually saw these pictures and heard these names was from George Sotomayor, because of his thesis on one-parameter families of vector fields. Had many discussions with him at the time when I first arrived in IMPA. But if you want to understand what happens here, in the two-dimensional case, I don't think they did what I'm about to do, but they used theorems of Poincaré about using the divergence as you come around. If this homoclinic point is stable, in other words, points nearby actually converge toward it, and you can see that situation would be when you have stronger contraction than expansion. So A plus B is negative. Then it would be stable. And when you bifurcate this across, it bifurcates into a stable limit cycle, okay, that's there, and then the unstable curve of the saddle will tend toward this. The stable will come in from infinity and, of course, be stuck. And that's your picture when the divergence, when the sum of these eigenvalues is negative. If it's positive, you have the reverse. I mean, it's sort of like you turn it around. Just take the negative of that, and you'll get an unstable. This type of situation in bifurcation theory, where you have a periodic solution, the period getting longer and longer, and then it disappears. In this case, it disappears to a homoclinic orbit, has a name. It's called the blue sky catastrophe. The idea, Charles would know much better than I, but the idea is that this periodic orbit is there, grows and disappears into the blue sky. Okay. The next example, so the beginning, this is where I really started. I've been trying for a long time, I had been trying for a long time to understand the bifurcation of, and the picture of Shilnikov's saddle focus. This has a name, Shilnikov's saddle focus. And what it is you have a vector field in three-dimensional space that has a hyperbolic critical point with a stable complex eigenvalue, in other words, real part negative, and a one-dimensional unstable curve, positive real eigenvalue. And in the Shilnikov case, where you get interesting dynamics, even before any bifurcation, when you have the homoclinic curve, you assume what they call the leading parts are positive. In other words, the expansion is bigger than the contraction. So the real part of the complex eigenvalue plus the real eigenvalue is positive. That's the typical. And in that situation, geometrically, what you see is that if you imagine that so here is where I came into the game. I was very interested in that problem, and I looked for proofs. And this was a while ago, maybe. I wanted to have proofs so I could explain it to my graduate student class. And I looked originally at Shilnikov's paper, and it's just an outline. It's like 3 pages long. And he says, and then you have this and you have this. So that wasn't a satisfactory proof for me, okay? And then I kept looking in various subsequent developments. And Shilnikov, of course, who was an expert in local analysis with analytic functions and changes of coordinates, would do things with his students that would produce a proof if the conditions that he stated were satisfied, and he would just say they were. There weren't really proofs of that. So I was talking with Charles Tresser about that. He had, I think, the same feeling. It was hard to find a decent proof. But if you look at the modern textbooks, for example, Guggenheimer and Holmes, they do this, but they make a simplifying assumption that the vector field is linear at near the critical point. In other words, there's a change of coordinates, if you want, that linearizes this. But in order to do this, you need to use this in this situation. It's very simple, actually. The fact that you have stronger expansion means that if you draw a little transverse section to the homoclinic orbit, this is now the unstable coming around and then spiraling in, a transverse section here, and you look at what happens nearby, small horizontal sections actually come up, the whole little rectangle here will come up and spiral, because when you're lower, it takes longer to get up, so you're inside and you're rotating. So it's easy to see that it will spiral geometrically like that. And the fact that the expansion is stronger than the contraction means that if you look at the first return match, so I've drawn some spirals transposed over here, that these horizontal strips that return to the sort of parabolic strips come from much closer to the stable manifold than away. So when they come back and do that, you see many horseshoes. And that was Shilnikov's first theorem about this. There are countably many subshifts on different symbols, and so you get infinitely many periodic orbits and so on. But to do that, you need differentiable estimates to measure the size. You don't actually have to prove hyperbolicity now. Okay? All you need is the geometry. Everybody knows that if you have a geometric horseshoe, you have positive entropy. And then if you want its 2 dimensions, you use Cat-Talk if you want to throw it in there. And then you have actual subshifts in there. So you don't have to worry about in modern terminology. And it gives you, if you're doing this to a low-level class, gives you the excuse to talk about powerful theorems. But the point is you need to have a differentiable linearization. So the assumption in Guggenheimer and Holmes is you have and in fact, you don't need a C infinity one, you only need a C1 one like that, okay? And so that's all you need to do this kind of theorem. And so generically, let me remind you, you always have linearization, and you have the following theorem. So by the way, this is for vector fields. I'm mainly going to talk about the associated problem for diffeomorphisms because of a technique of Sternberg. A vector field, and let's keep the same smoothness. Usually for him it's at least C2 or C3, maybe higher, CK, where K is bigger than or equal to. In this theorem, it's 1 even. If you had C1 as far as the vector field is concerned, it's linearizable. There's a change of coordinates that makes the vector field linear if and only if the same is true for the time 1 map. And so you can, and that's a stronger theorem, okay? So you could, it's better to talk about diffeomorphisms, and then you also get the same theorem, of course, in transverse sections for periodic orbits. So here's the statement, a version of Sternberg's theorem. For smooth linearizations and diffeomorphisms, there are these things that are called non-resonance conditions. So you will find in Hartman's book, for example, if I have a linear map, L, from Rn to Rn, that's supposed to be the linear part of the vector field with hyperbolic singularity at the origin, and the eigenvalues with multiplicity listed as lambda 1 up to lambda n, and then you take the vector field T, later on this is the map T, so this is a linear automorphism, okay? And you add a nonlinear part. That means that the value at 0 is 0 and the derivative is 0. And if this is Cn, okay, and you give me an M, you want an M times a CM linearization, there is an N, depending on this smoothness of the linearization desired and the eigenvalues, such that if these things, if you have this map and the n jet, the first n partial derivatives of f are 0, so up to order n it's linear, and you have then you have a linear change of coordinates. So you lose derivatives, okay? That's actually not the way Sternberg stated it. He stated it this way. He stated you have these non-resonance conditions because that allows you, by standard techniques that go back to Poincaré, to make the n-jet linear, to just kill all the other terms if you have these so-called eigenvalues. When you try to change coordinates for the vector, I keep moving back and forth because my application is to the vector fields primarily. But no, in the map case, as long as you make the n-jet of the diffeomorphism T linear up, the n-jet linear, so all the terms up there, then there's a CM linearization. So this is useful. It's generic property, it's useful, and so on, but it doesn't quite do what Shelnikov's thing needed because there was no genericity. So I was interested in trying to go lower and see if I could do something about C1 linearizations without these conditions, okay? And so I went back in the literature, of course, and in this context, there are such theorems, well known for a long time. The first one in this case was also due to Sternberg. In the line, you have a In the line, if you have a hyperbolic fixed point for a diffeomorphism, okay, and the diffeomorphism is at least C2, then there's a C1 linearization, is the way his early paper was stated. Later, he proved that, in fact, you don't lose derivatives. There's a CR linearization as well, like that. So that's the first theorem in dimension 1. Then we go to Hartman in dimension 2. If you have a it's usually stated that if you have a C2 diffeomorphism and a hyperbolic saddle fixed point, so eigenvalues outside, absolute value bigger than 1 and less than 1, then it's C1 linearizable. But if you look at Hartman's paper, it's actually C1 plus Lipschitz. C1-1 is what I will call. Then you have a C1 linearization. He actually, I'll go further on that, so that's the next theorem. And then the remaining theorem, which is very beautiful, is the same theorem is true for arbitrary contractions. If you have a C1-1 map with a fixed point at the origin, and the derivative is contracting, all eigenvalues inside, then in fact you have a C1 beta linearization where beta is a positive constant. So you can make the linearization C1 with its derivative Hurlder continuous. Those were the theorems that were around. Actually, in his paper, notice I didn't say C1 here. I said C1 beta. So in fact, Hartman claims in the saddle case, and I'll talk about this a little bit more, but he claims that, here's what he does for the saddle case in the C1 case. He does some analysis, and the statement of the theorem is you have a C1 linearization. Then in the remarks, he says that you can modify the proof to make it C1 beta. If you actually look at the proof of this theorem in his paper, he doesn't even prove C1. He proves that he got bored by the time he got to this part of the paper, because by that, at that time, I believe his main interest was for contractions, which were general in n-dimensional space. So he actually only proves that the linearization is continuous and says, it's the same argument. You can make it C1, and you can modify the proof to make it C1 beta. Well, the truth of the matter is, I had never seen, so let me go further, and the natural question following this is, can you do it with weaker regularity? Instead of C1-1, can you do it, say, C1 or C1 alpha? That's one type of generality. Another is infinite dimensional spaces. Can you do a similar kind of linearization theorem in infinite dimensions? And so the first answer to the first question is, if it's C1, can you C1 linearize? In the old papers of Sternberg, he provides this example that shows you can't. You cannot. And there are technical conditions in C1 that will allow you to do it. I don't have time to talk about them. So here's an example on the line from Sternberg's paper, which says that this map is C1. It has a contracting fixed point at the origin, but there's no C1 linearization. So the natural question then is, okay, let's give a little more and do C1 alpha. So consider that. Now, I'm going to do this in finite dimensions, but actually in Banach spaces. And this brings me to an observation. You know, I did all this, I knew what I was working on at the beginning, but if you go back to the title of the talk, it's one-dimensional dynamics. And I thought to myself, what am I doing that has anything to do with one-dimensional dynamics, right? And then I realized that what I'm actually doing is, what's the main part? If you ask somebody, if you know nothing, and you ask somebody about the main part of one-dimensional dynamics that makes it different from higher dimensional dynamics, and to me anyway, I'll ask the experts if they agree, it's that in the derivative along an orbit expands at the same rate everywhere. If you go to 2 dimensions and you had it conformal, so it expands in the same way everywhere, you can do something similar, but it's not persistent and not generic, right? And so having the derivative expand the same in every direction is more or less one-dimensional. That's what I'm going to talk about. And it's going to happen in a Banach space, going to happen in others. But it's really one-dimensional in that sense, although techniques are a little different. I'm going to need to use bump functions in the Banach spaces. In finite dimensions, there's no problem. If you have a smooth norm, you have a smooth bump function. But I learned as I was doing this, I knew vaguely smooth norms weren't so consistent, but there's a whole theory about when Banach spaces have the smooth norms. And it turns out that they have to be reflexive, for example. And the LP spaces for p bigger than 1, as p gets bigger, you have smoother and smoother norms, but even for p bigger than 1, you have a C1. You have a C1 norm and its power is Hurlder continuous. That means you have bump functions. And so you take composition of the power of the norm with a smooth bump function on the line, you get bump functions. That's the kind of thing I need, and it is a special condition. So right now my theorem won't work on things like C01 or L1, which are not reflexive spaces. Okay, so I'm going to now go to the definitions and then come back more to the motivations later. So all my Banach spaces will be real, and they will be C1 alpha. That means they have C1 alpha bump functions. Alpha is between 0 and 1. I'm going to let L of EE be the bounded linear maps with the sup norm, automorphisms, invertible bounded linear maps, and I'm going to let rho of L for such an automorphism be the spectral radius, which you usually define, you can define by complexifying and taking the largest absolute value in the spectrum, or you can do it this way for automorphisms. You take your norm. This becomes independent of norm then. You take the norm and you take the limit of L to the n to the 1 over n, like that. The norm L to the n to the 1 over n. And that will define a spectral radius, actually even for maps as well, but then you have to work a little bit. Here you'd use the usual subadditivity and you get a theorem. So given alpha between 0 and 1 and an automorphism to start with, I'm going to say it's contracting if the spectral radius is less than 1. That just means that some power has norm less than 1. Okay, like that. It's a bounded automorphism. It's expanding if the inverse is contracting, okay? It's alpha contracting if, so here is something, rho inverse rho L. That I will call actually the spectral condition number. In computer science, if you take the norm of an operator and the norm of the inverse and the product, it's always bigger than or equal to 1. And that's called the condition number. So this will be the spectral condition number, but I won't use that term anymore. And this number is less than 1. So that means that it's contracting, right? Because rho L inverse rho L is bigger than or equal to 1 everywhere. How do you see that? You just take t to the n times t to the n minus n. That's the identity, right? The norm of that's less than or equal to the product. Now take 1 over n and take the limit. So the spectral condition number is bigger than or equal to 1. This number being less than 1 requires then that the spectral radius of L to the alpha is good enough to kill something bigger than 1, so it has to be contracting. This only occurs. And if in finite dimensions, this will imply, maybe infinite dimensions as well, that the spectrum is contained in the largest eigenvalue, which is rho of L, and rho of L to the 1 plus alpha. So a little band around the actual circle that contains the spectrum. Okay, alpha expanding means the inverse is alpha contracting. Circular. Circular means that the spectral condition number is 1, okay, like that. And that is essentially what I think of as one-dimensional. It means that in finite dimensions, the spectrum is in a single circle. Everything is expanding by around that and contracting. That's really actually one-dimensional in some sense. So it actually does have something to do with one-dimensional dynamics. Bicircular will mean that you have a direct, it's hyperbolic, and it's included in the definition. You have a direct sum of an expanding part and a contracting part, and each one of those is circular. So you have two circles that contain the spectrum in finite dimensions, okay? In infinite dimensions, I don't know. But two circles that contain the spectrum where one of them is inside the unit circle and one of them is outside. That's the bicircular situation. Alpha hyperbolic will be something that is a little bit thicker, a little band around a circle inside the unit circle and a little band outside the unit circle. So the precise definition is you take these condition numbers, which are bigger than 1, and you look at how close the eigenvalues are. I'm thinking of finite dimensions, but the proper definition is in terms of the spectral stuff and so on, how close they are to the circle. Some people call that the skewness. That has to be something that kills the other, so it has to be less than 1, the alpha power. So the contracting part is far enough away from the circle that it kills this condition number, and the expanding part made inverse, its inverse spectral radius, is far enough away to kill those things. And the observation that's obvious, so the tau alpha is the maximum of the spectrum of the contracting part and the spectrum of the inverse part, which is contracting as well. So it's something less than 1, okay? So it's obvious that if the map is bicircular, it's alpha hyperbolic for every alpha, right? Every positive alpha, like that. And so now I'm going to do this for fixed points and basically state the main theorem. So I take alpha less than 1. I take a point in my, now I'm in the Banach space situation. I take a neighborhood of that, and I have a diffeomorphism, which is C1 alpha with a fixed point. And it will turn out to be hyperbolic because the fixed point will be, the derivative will be alpha hyperbolic, and hyperbolicity with a little bit more, a thin band around the spectra in both the contracting and expanding parts is alpha hyperbolic. Okay, so the nonlinear part will be C1 alpha, okay? And the fixed point is called alpha hyperbolic, I just said it. It means that the linear part is a hyperbolic, alpha hyperbolic automorphism, and the nonlinear part just is C1 alpha as a map, okay? And similarly for vector fields, you say that a critical point is alpha hyperbolic if as a fixed point for the time 1 map, it's alpha hyperbolic, the obvious thing. So here is the main theorem. Let's take an alpha hyperbolic fixed point of the local C1 alpha diffeomorphism, okay, T. Then for some beta between 0 and alpha, T is C1 beta linearizable near the origin. And moreover, and this is important for my applications, the linearization will vary continuously. It probably is smooth, but I didn't need that, so I didn't bother doing it like that. And the main reason, by the way, that it will vary continuously is I simply reformulate these things in terms of contraction maps. And it's known that if you have contraction maps that depend in reasonable spaces that depend on a parameter continuously, then the fixed points depend continuously. Okay, so that's the main theorem, okay? And a similar theorem for vector fields. So if we go back to the Shilnikov example, that is in 3 dimensions, and if your map is C2, then it's, or your vector field is C2, it's C11. So actually Hartman, except he didn't prove the continuity, but I presume he could have, he just didn't do it. But Hartman's methods will actually work in that case because you have C11 in 3 dimensions. We'll talk a little bit more about something that became interesting a little later. I'll always assume my critical points or fixed points are at the origin in the Banach space. So the motivation was what I told you. I was trying to do some version of Shilnikov, but after I did this, I realized that in some sense it was a much more interesting theorem, and here is why. Let's take an arbitrary hyperbolic fixed point, okay, for a diffeomorphism. CR, R bigger than 1, and this is in finite dimensions right now, where R doesn't have to be an integer. It could be C1 alpha. R is something bigger than 1 where you just have Hurler continuity of the derivative, okay, like that. And with the hyperbolic fixed point, let's break up the eigenvalues into a central part. These are the eigenvalues of norm closest to 1, and then the rest. So it's like linearly you have a normally hyperbolic subspace, and then the rest. That's what this means. The LC is the center part, which doesn't have to be 2-dimensional, by the way. It's just constant spectra, right? All eigenvalues, Shilnikov would call these the leading eigenspaces. And LSS is the remaining eigenvalues, which are norms strictly smaller than those, LUU strictly bigger, okay? So notice that the central subspace is a bicircular subspace, because here you have a subspace where the eigenvalues lie in 2 circles, inside and outside, right? And outside of that, you have normal hyperbolicity, like that. So we have enough knowledge of invariant manifolds now to know that there is a central manifold tangent actually to any sort of section like that. But I'm interested in the one that's closest to the origin and norm, the places, the bicircular part. I call this the Lyapunov center subspace, but or central subspace. Shilnikov would call it the leading subspaces, like that. That is bicircular there, and with invariant manifold theory, we know you have invariant manifolds, C1 manifolds, that are tangent to that subspace, and generally they are not C2. If your contraction is strong enough and your expansion normal is strong enough, then you will make them C2 or CR. But in the general case, if the eigenvalues that are near the leading ones are close to it, the map will only be C1 plus alpha on these manifolds. You can linearize on these manifolds. And that has implications not so much in 3 dimensions, but look at a Shilnikov homoclinic orbit. In higher dimension, you always have a central subspace, and typical homoclinic orbits will miss the strong stable and strong unstable manifolds, right? They'll miss those. And so they will come in. In fact, you can actually show that the orbits you can find, and I'll show you this in a minute, you can find C1 alpha submanifolds which contain the orbits. So you can restrict to a center manifold and linearize there, and you can therefore simplify a lot of arguments in higher dimensional homoclinic curve bifurcations. Okay, now I will mention the proofs of those theorems, which I didn't find early on, I found later in a book. There is a 2-volume series of books by 2 Shilnikovs, Andrei the son, Leonid the father, and Schwa, the electrical engineer at Berkeley, and Dmitry Turayev. They wrote 2 volumes of books, and in there you will find a proof that's good enough to do these kinds of things using recent results, more recent, like maybe in the 90s, I don't remember, of Ovsyannikov and Shilnikov, where they get a kind of a normal form. They assume the vector field is CR, but in the center they get a normal form. It's not linear, but it's good enough to do something. I like the linear ones and the ones I get because sometimes, for example, in the Lorentz system, it's interesting to know the size of the domain where the thing is linear. And in my case, it's very transparent how you do that. In these other cases, it's more opaque. I'm sure it can be done, but it's more opaque. Okay, so that was, for me, what made my theorem much more interesting, right? I was trying to figure out why it was good for something, and this actually made me happy. Okay. So you have these manifolds. They are typically, if the eigenvalues are close, now the actual, I talked to some of once I found C1 alpha and I had it in a Banach space, I had to walk down the hall and ask my PDE friends, because I know they study things like the almost linear, semi-linear heat equation and things like that. And I asked them, are there examples where you have C1 alpha maps in your C1 alpha semiflows that aren't better? And they said, oh yeah, here they are. And that's something I have to learn about when I go back, because I didn't understand exactly. Actually, I understand a little bit about how you do it in terms of like the nonlinear heat equation with other right-hand sides. But if there's anybody here who knows about those things, I'd be delighted to discuss that with you, because I think this will help handle bifurcation problems for these PDEs, okay? Now, the next question would be, in 3 dimensions, so Hartmann's theorem, go back to Hartmann, C11 implies C1 beta linearization for a saddle point. If you go to 3 dimensions, is the same kind of theorem true? Do you get something like a C1 linearization? And Hartmann gave this example in his paper, where you have he did it in the vector field case and in the diffeomorphism case, but since I talked about vector fields, here's a case where you have a resonance of order 2. You look at a vector field in 3 dimensions with eigenvalues 2 negative, A less than B, and then the positive eigenvalue is B minus A. Okay? In other words, the sum, if you look at the middle one, B, it's the sum of the smaller and the taller. And he proves in this case there is no C1 linearization. It's interesting, actually, in the linearization theory, if you make this one assumption that they're different, in other words, the smaller plus the bigger is not equal, then you get an analytic linearization. That's I forgot to mention, in the beginning of the paper, I mentioned this. This paper is on the archive, so you can download it there if you're interested. So now let's look at what actually started me on this. It was the Lorentz equation, to try to understand when you're passing near the critical point at 0. And this is for parameters where the rho parameter is bigger than 1, and usually beta is minus 8/3 and sigma is 10. The standard Lorentz, but with a rho varying where you have a saddle point at the bottom and you have 2 critical points outside, other critical points. It was to understand these return maps where you take a transverse section. And so now, how does this fit into this theory? And this was actually my motivation to do it. If it were linear in a whole neighborhood, you have the standard estimate that if you look at the, I'm sorry, I can't get the, if you look at the, a curve through here, and you push it down until it goes here, and you let the x-coordinate be the distance here, x1 coordinate like that, and you go down here, the height as a function of x1 is like x1 to the alpha, where alpha is the ratio of the eigenvalues. We've heard many talks about that as motivation here at this talk, at conference and so on. It's an easy estimate to do that if it's globally linear. Well, in fact, you don't need it to be globally linear. Here was the motivation. You don't need linearization in a whole neighborhood, so the way this started was I took that curve and iterated it forward, and you generate, in that situation, an actual invariant manifold, which in the Lorentz actually turns out to be C3, C8, something like that, because the contraction is strong enough. And so we were interested in trying to do a modification of the local part of Tucker's theorem with a graduate student, and here you can use Hartman's theorem plus continuous dependence of the thing, because you take this thing, this manifold goes down, you get an estimate. You move the curve a little bit, you go down, you get an estimate. You would like to know that the estimate is close to what you had before. You have the same constant in the power to the ratio, and you do because it's continuous. You can linearize in the manifold and make it continuous. So this actually applies to give nice estimates. But in fact, if you had extended Hartman's theorem to the continuous dependence, the applications like this to this part of Lorentz, and also to the part where you have the homoclinic butterfly around 13.92 or something like that, that's referenced in Sparrow's book. All of those cases would be covered by Hartman's theorem plus continuous dependence. But it's not at the back of my head. I really wanted to do it in the case where you didn't have strong contraction and smooth invariant manifolds, and that's what led to this theorem. And so any kind of hyperbolic saddle point, you can create this center manifold, which is C1 alpha in general, and then linearize on it in a continuous way. Okay, I was going to give you some idea of the proof. Now, let me just say that the C1 linearization of this, some people have heard me talk about the motivation here and that as much as 2 years ago, I think in Paris and other places. And it started with two-dimensional diffeomorphisms, and it used Journet's theorem and so on. And it gnawed at me that I couldn't seem to get Hartman's theorem. I went back and tried to, where it wasn't 2 dimensions, it was just bicircular, like in 3 dimensions. I couldn't do it because it wasn't the same I used absolute continuity of foliations, those kinds of things, so it bugged me forever. And then I finally found a simple way to do, relatively simple, to do the general bicircular case, but only C1. And I had that about 2 years ago, or 2.5. But Hartman in his paper said you could do it C1 beta. He didn't do the proof of C1 beta, but he said so. So I feverishly started looking around for somewhere where somebody proved C1 beta, and they never did. So as far as I know, the C1 beta linearization, my proof is the only one that will be available in the literature. If you can find another one, I'd be delighted. Now, I will say, if you assume C1-1, there is even the linearization paper of Ciccone and Swanson only claims C1 linearization. There are a number of people who've done generalizations to Banach spaces I don't have time to talk about, but they're in the paper, all the references in the introduction to the paper. So let me tell you in the 5 minutes, 5 or 4? Oh, I have 10, good. So let me tell you the thing I like about this proof, the thing I love about the C1 part is if you lead people through it, you could give it to graduate students as an exercise. I will convince you of that. It's really elementary. And then I give you my little story about all the time and agony and work it took to get C1 beta, which in the end is still pretty elementary, but it involved a number of little tricks and so on. So, and I could see why Hartman, if he knew how to do it, by the time he wrote that paper, didn't want to bother, because you have to change a lot. Okay. So here's the standard way you do this kind of theorem. I'm going to assume L is a hyperbolic automorphism, okay? It's alpha hyperbolic, you'll see why in a minute, which means it's almost bicircular. The linearization will be the identity plus phi, where phi is the right regularity. In this case, C1, the value at 0 is 0, and the derivative is 0. So you take L of the linearization times the linearization, and then t, which is L plus f, and you expand it out. As I will say later, because the slide, well, let's go ahead. I mean, let's just, okay. This presentation of this kind of thing is standard in linearization theory. They do some version of this, not always this way, but some version of this. I do it this way because you'll see the operator I have to deal with is linear. It's not just Lipschitz and so on, or Lipschitz close to linear, it's actually linear. But the globalization ideas and so on are very similar to the Grobman-Hartman proof that was given independently by Pallas and Pugh, you know, way back and so on. But that was C0, this is going to be C1. Okay, so the idea here then is you look at L of R, call the R, I plus phi equals R times T, which is L plus F. You expand it out. This is L plus L phi. This is L plus F from I and phi L plus F. The first L's cancel, and then you get L phi equals F plus phi of T, which is L plus F. Invert, multiplied by L inverse, you get phi equals L inverse F plus L inverse phi of T, this. This is linear, it's a linear map. This is an affine map. And the idea usually in the contracting case would be to prove this is a contraction on a suitable function space. If it's hyperbolic, you want to prove this is a hyperbolic automorphism on a suitable function space with the right conditions. So I want to write this, I call this the algebraic problem, right? This operator is H, so phi minus H is this, and the identity minus H of phi is L inverse of F. You set up a Banach space of functions, phi is suitable functions, and you want this operator to be invertible. So if it's a contraction, it's obvious. If it's hyperbolic, has a direct sum decomposition, on one part you take H, the other part you take H inverse. This is invertible in the space, and you get your linearization, okay? So let's move on. So now let me define the function space in this situation. For C1 functions, I'm going to look at the horizontal coordinate and the vertical coordinate. That's going to be phi and psi. So the picture is, I have my original linear map, and this one's going to be expanding horizontal. That's going to be, this is EU, this is ES. I'm going to take the standard identifications with the product like that, okay? And I expand here, I contract here, and then I have, so that's L, and I have L plus F. And now here's my function space. I want it to be C1 functions, which, well, there are a couple of, I want to define there are a couple of steps I have to do first, okay? In the slides, I have done the definition of the function space, but to use them, I'm going to have to do more. So my horizontal subspace, infinite dimensional space ES, is going to be where it's going to, okay, let me just say, using a bump function, I can assume the first thing I have to do is the contracting case. So let me go a little further up here, okay? First thing I have to do is the contracting case and work on each space. I did this independently, and the proof I give here more or less works, but then I found out later that a C1 plus alpha diffeomorphism with a fixed point at the origin, C1 alpha, which means the linear thing satisfies the rho L inverse, rho to the alpha, has a C1 alpha linearization with no loss of derivatives. And that was proved by Marc Chaperon in papers that I didn't know about when I started on this, okay? So we can use that. So the first thing you do is you flatten, you use invariant manifold theory. You get a C1 alpha stable manifold, a C1 alpha unstable manifold, you flatten them out. Okay, so I can assume the local stable and unstable manifolds by a C1 alpha coordinate change are in the subspaces. Okay, on each subspace I linearize using chaperone or using the proof I give in my paper of that. Okay, so now it's linear on each subspace and local. Then you globally extend so that it's linear on each subspace. Okay, Lipschitz close to everything, and this is very important for this, vanishes outside a small neighborhood of the origin, and that neighborhood's going to shrink as I need it to work. So that's the assumptions I'm working with now after preliminary constructions. I assume that I have the map as a global diffeomorphism, C1 alpha diffeomorphism on the Banach space with a fixed point at the origin, C1, alpha hyperbolic, linear part, and it's linear on the stable and unstable subspaces, okay, which are invariant by T, and on the complement of a small ball. And so now let me tell you what the function spaces are. So my functions, which will be, I have maps from the whole space, EU plus ES to EU. That's one set of functions. That's what I'm going to work with here. And then I have maps on the whole space that map to the other space like that. My candidates for the linearization being I plus that. They map into here, they map into there, okay? The coordinate functions of my candidate for the nonlinear part of the linearization. Okay. And since I've linearized along these manifolds, the choices of the nonlinear function I have, f, is very special. It vanishes along the union of the stable and unstable manifolds and outside a small neighborhood of 0. And so that's what I'm looking at here as candidate functions. Functions to the unstable subspace on the whole space, which vanish on EU union ES together with the outside of a ball. That's what I stated in the next slide. And here I wanted to find a norm on that. And this was motivated in large part by really understanding what Hartman did in the contracting case and so on. And that is, I defined so I'm going to look at functions to EU. And here's the norm. The maximum, the x derivative over y to the alpha, okay, and the y derivative over x to the alpha, and where these things vanish, the numerator vanishes anyway, so you might as well assume that they're 0. That's gamma 1 and gamma 2. That's used to find this coordinate, the horizontal coordinate of my nonlinear part of the linearization. The vertical part is the next two, which I won't have time to do, and then you take the norm being the sum. So here's my direct sum of spaces, the candidate functions, which are finite in this norm. The x derivative grows like a constant times y to the alpha, the y derivative like a constant times x to the alpha, uniformly bounded on the whole space. Okay, so let's move on. That's where I am there. And then you use these facts. Let me just go on since I don't have much time. Where does the alpha hyperbolicity come in? So here are my conditions for alpha hyperbolicity. And let's think of this as the spectral radius of B is strong enough to kill this. And this is the spectral radius of A inverse is strong enough to kill the B stuff. This is used for the functions that go into ES. This is used for the functions that go into EU. And I have spectral radius conditions. I write them down here, perturb them just a little bit, and then take the nth power of this, and I have these conditions. So ultimately, I'm going to use these conditions to show that the nonlinear map, which is L inverse phi of t, is a contraction on ES and an expansion on EU. So it's hyperbolic and you do it. Well, I don't have time to really go through much of this in detail now. So let me show you the easy, once you set it all up, here's all you have to do. And this is why I think it's a graduate student exercise. You want the x derivative. So why do I have a power? Because my first power of the map wasn't enough to give me the estimates because I'm doing spectral radii and not norms. So I have to take a power so that I can use the power where I get these conditions working. So the theorem is you do the same thing for the first power. That proves that your maps are bounded linear. Then when you go up to the nth power, where I had this condition right here, you get the contraction conditions at the nth power. Okay, so let me just briefly show you this type of argument. I won't have time to go further. The x partial is supposed to be estimated by some power of the y to the alpha. So let's look at the x derivative of this h to the n. And h to the n I'll write as a linear part up here, an and bn, and then nonlinear parts, xn and yn, and call the whole business u of xy and v of xy, right? That's what your t is in there. This is a inverse phi of t. The only reason I'm able to just use an is I'm looking at values in the EU. For bn, you do the inverse. Okay, so now I want to estimate this x derivative, and I want it in terms of y to the alpha times the norm of phi times something less than 1. So look at this estimate. You use the chain rule. You take phi sub u ux plus phi sub v vx, and now the norm, remember, was the u partial divided by v to the alpha, the x partial divided by y to the alpha. So you want to see the norm, so you divide by v to the alpha, multiply by v to the alpha times ux. Divide the next part, the y, divide by u to the alpha, multiply by vx. Now just look at this. This guy is the norm. This guy, v was b y plus a nonlinear part. The nonlinear part by my conditions is epsilon times y. So this is b to the n plus epsilon times y to the alpha. That's the b to the n plus epsilon, which kills the a inverse and the a, right? So this actually turns out to look like the first part of my norm, which was the gamma 1, times this turns out to look like, look at this. There is your estimate. A to the n, ux is a plus epsilon. Okay, you have a to the minus n, a to the n, and you have b left out an alpha. No, it's all in there. No, it's fine. by to the alpha. That is less than 1, right, times y to the alpha. So this part is less than 1 times y to the alpha. The other part uses the fact that my nonlinear parts are 0 off the radius delta, so there's an x to the alpha in that part, but that's less than delta. So given all this stuff, I just make delta small enough so that doesn't affect the fact that this thing was less than 1. So the whole thing, the sum of these, is less than 1. That's your contraction in the x variable. Do the same thing in the y variable here, and you use the similar estimates here. In that case, the u derivative, the gamma 1 will be small, it'll have the delta in it, and the other one will be less than 1. And so really, once you set this up and you see what you want to do, this is a very standard, simple estimate. Okay, I'm more or less out of time. So that, as I said, I had, and the one for the other direction is similar. I had that about 2 years ago, and I kept fighting to get the nonlinear part. What was I trying to do? As my wife tells me, I am a stubborn man. And so when I think I can do something, I just keep trying to do it. I got a global linearization here by something that was Lipschitz small and controlled on the unstable and stable direction. So must be able to get a C. Hartman said you can do it, C1 beta. Said, damn it, you can do it, C1 beta. Do it on the whole Banach space again, trying and trying and trying. And here's where, in a nutshell, the problem comes. When you do Hölder, you have to use, like in one variable, not x, but x plus h. And the x might be 0 by this bump function, but the h isn't. And if you try to make h small, the fact that you expand, you lose your estimate. So how do you control the Hölder part of this? And I kept thinking I could do it, and it kept failing and failing. So I gave up, and I said, okay, I'm going to write the paper as it is. And I waited, came back to actually get it organized. And then I realized the following thing, which probably Hartman, being the smart guy he was, knew anyway. You don't try to linearize in the whole Banach space, because you don't need it. So what you do is you take a neighborhood of 0, and you look at the forward orbit of it, like that, and you look at the backward orbit of it. And going forward, you use your first function, psi. The one had values in there. And because when you go outside of the ball of radius delta, if you look at a function that vanishes here, that vanishes there. When you take the image, it still vanishes. So your mapping, which is A inverse phi t, is well defined. Otherwise, it's not. You lose the fact, I mean, if you looked at the whole Banach space and look at orbits, you go way out to infinity and you don't control anything in the Hurley part. So this is invariant. So then you use that part to do the linearization in that neighborhood, and you use the inverse to do the linearization in the other neighborhood. Take the so I get a C1 beta thing in this big space for the maps with values in EU. I get a C1 beta in the backward orbit of this in this space for the maps that intersect them. You get both of them C1 beta, right, like that, and you're done. And once you have them C1 beta here, you can do it on bounded iterates, because composition of C1 betas is C1 beta like that. But this takes some tricks to do, so it became much more technical and much more complicated at the end, but I was happier. Thank you very much. Okay.